Hello, welcome to a new lecture of communication lecture series. So in this video I am going to start a new topic that is pulse modulation systems. So you have some basic idea of analog modulation, that is like amplitude modulation, frequency modulation, where we can use continuous time sine and cosine wave. We can use continuous time sine and cosine wave as of very high frequency as carrier signal, right? So but in pulse modulation system, the carrier is no longer a continuous time signal, but it consists of a pulse stream like this. So it's like having 1-0 rectangular wave, right? Just like clock signal, So this is pulse stream, right? So in pulse modulation system, the carrier will be like this. And what is the concept of pulse modulation? So pulse modulation means we are going to embed. So we are going to transmit the message signal. We want to transmit the message signal, but we are not going to transmit the message signal directly. We are going to modulate the pulse train. So how we are going to modulate the pulse train? We are going to modulate some parameter of the pulse train. So some parameters of the pulse train will be varied according to the message signals. Okay, and what are the parameters? Parameters are like amplitude, width and positions. Okay, this amplitude, this width and the position of the pulses will be varied or modified according to the message signal. Okay, so now let's say some of the example of pulse modulation techniques. So let's consider suppose this is our message signal. Okay, suppose this is our message signal that we are going to want to transmit over the channel. Okay, but we are not going to transmit the message signal directly. We are going to transmit a modified pulse stream, okay, which will be varied according to the, so pulse train will be varied according this GT, that means the message signal. Okay, so here what is happening, this is called pulse amplitude modulation. So here you can see the amplitude of the pulse is varied according to the magnitude of the or amplitude of the message signal, right? So you can see its amplitude of the pulse train is varied according to the amplitude of the message signal. So that's why it is called pulse amplitude modulations, and you are going to transmit this PAM signal through the channel, right? So this is one example of pulse modulation system. Second, you can do pulse width modulation. So obviously the name suggests that the width of the pulse will be varied according to the magnitude of the message signal. So here you can see the width of each pulse are varied according to the message signal. So when the magnitude is maximum, width is maximum. Okay, when magnitude is minimum, just like the negative one, here you can see the magnitude, the width is minimum. Okay, so width of the pulse train is varied according to the message signal, and we get at the output we get a pulse width modulated signal. Okay, similarly we can generate a pulse position modulated signal. Okay, so here you can see the position of these pulses are varied according to the message signal. Okay, so you can see that each of these pulse positions are varied, okay, from the reference point, okay, and according to the message signal's magnitude. Okay, so this PWM and PPM are together also called pulse time modulation, PTM. Okay, PTM, pulse time modulation. This PP. So PW and PPM are the subclass of PTM, pulse time modulations. Okay, so these are some basic definitions, that is or basic type of pulse modulation system. Okay, now we are making a transition from the continuous time carrier signal towards pulse time modulation. So continuous modulation to pulse trend modulation, right? Pulse modulation. So what are the basic advantage? What are the potential advantage of this pulse trend modulations over, or pulse modulation system over continuous wave modulations? So the first thing that I would like to mention that here in pulse modulation system, you don't need to transmit the power continuously. Okay, so here so what you are transmitting actually in pulse modulation system, you are transmitting a modified train of pulse, right? Suppose you are transmitting a PAM signal, pulse amplitude modulation. So you are transmitting a modified impulse train like this. So you can see that here the transmitted power being concentrated in this region, in this burst region, where the magnitude is 1. It has a finite magnitude, and rest of the time it has very low magnitude, right? 0. So there is no need of continuous power generation in pulse modulation system. Okay, so this is the first advantage. And second advantage is that in pulse modulation system, the multiplexing is possible, particularly the time division multiplexing is feasible. So basically the time interval between the pulses can be occupied by samples from other signals, allowing the advantage of time division multiplexing. So what I mean basically is that the pulse modulation system permits the simultaneous transmission of several signals on a time sharing basis, and that is called time division multiplexing, because a pulse modulated signal occupies only a part of the channel time, right? Because you can see there is lot of space between each pulses, right? So we can transmit several pulse modulated signal on the same channel by interweaving them, and that is called time division multiplexing, and that is one advantage. So we are going to discuss this time division multiplexing in the subsequent lectures with much more details. So it's for this timing, it is worth noting down that this time division multiplexing is possible using the pulse modulation system. Okay, but one downside of pulse modulation system is it requires a very large amount of transmission bandwidth. Okay, so very large amount of transmission bandwidth, and compared with the message bandwidth. Okay, so we are going to discuss this thing also in great detail in the subsequent lectures. May not be maybe in the next lecture. So this is one point. Okay, so this is one downside of or one disadvantage of pulse modulation system. Okay, now I will be focusing on mainly on the most important form of pulse modulation, that is called pulse code modulation, and or PCM, right? So PCM basically a tool for converting an analog signal into a digital signal, right? So here at the input of the PCM system is you are having a continuous time analog signal in the input, and in the output you can see it will produce a bit stream 0 1 1 0 and so on. It's like a bit stream, digital data it will produce. Okay, so the essential processes of this PCM are first the sampling, then you are having a quantization unit, quantizing, and finally you need a encoding block. Okay, so I am going to discuss this each block one by one, and then overall I will one by one, and some of the things you already know from your digital signal processing class, and some of the base, particularly the sampling things we already covered. So but I will just give you a overview of the sampling process. Okay, so let's move on. So sampling, so you know the sampling is simply means so ideal impulse sampling means you are input to the system is input to the system will be a continuous time signal, and it will be multiplied with a product modulator or a multiplier with a impulse train that is also called Dirac-Combe function, right? This ST is Dirac-Combe function, and it will produce a, so this is my Dirac-Combe function, and it will produce a sampled version of the input analog signal, right? So this is a discrete time signal it will produce. But suppose my sampler, so you already know that Nyquist criteria or sampling theorem, right? So that is called, so suppose my sampler has the sampling frequency, sampling rate that supports its Fs. So obviously it will according to sampling theorem, my input signal must be band limited to Fs by 2, right? It should be band limited to Fs by 2. Okay, so to do that, because we know that, so according to Nyquist criteria, the Fs should be greater than equal to twice of Fm, where Fm is the maximum frequency present in the signal. Okay, so to make it band limited to Fm, that is Fs by 2, we are going to use a low pass filter, that is, okay, this low pass filter is basically the also called anti-aliasing factor, because if right other so if Nyquist criteria is fulfilled, then we can reconstruct the analog signal, this analog MT, we can get back my MT from the sampled signal Ms of t if we obey this Nyquist criteria. That means F is greater than 2 Fm. Okay, and to ensure that this is satisfied for my system, my sampling system, I need to pass the input signal through a low pass filter to make it band limited to Fs by 2, that is the maximum frequency possible. Up to that we can reconstruct it. Up to that my system will be able to reconstruct the MT from the sampled signal, right? So this is the basic idea of sampling, right? So you know that how to derive all these things, all this criteria, how the spectrum look like, the baseband and the replica, what is the spectrum of this how to draw the spectrum of the band limited signal MT, and how to draw the spectrum of this sampled signal. You know all those things, so I'm not going to cover that again. So if you have any doubt, please let me know. Okay, so basically you need two things in sampling process. Sampling system at two things. One is this low pass filter, that is basically anti-aliasing filter, because it's prevents the aliasing, okay, by making the MT band limited to fs by 2, okay. And we need another multiplier where one input is, where the MT is multiplied with the low pass filtered MT is multiplied with the Dirac-Cohen function, and finally we get a sampled signal, right? So another aspect is that you already know, but since we are discussing this thing, so I would like to cover. So this is reconstruction. So we can by this process, by sampling process, ideal impulse sampling, we can get the sampled data from the analog signal. Now suppose I want to reconstruct back, we can reconstruct back my sample signal, my original MT from the sample signal. Then I have to use a reconstruction filter. That is basic. So that is basically a low pass filter. So the frequency domain representation of this reconstruction filter is basically a low pass filter, whose so that is from fs by 2, whose passband is given from minus fs by 2 to fs by 2. I think magnitude will be here the ts, okay, magnitude will be ts, okay. So that is one correction you should show. Its magnitude is not 1, but its magnitude will be ts, that is not given. So obviously so this is a LTI system. So filter, it is a LTI system. So if I do the impulse Fourier transform, we'll get a sinc filter. So h of t will be sinc of fst. So this is called sinc filter also, right? So this is the impulse response of this filter. So the output of this filter will be just the convolution of MST and this h of t, right? And we'll get this type of expression, okay. So we'll get this type of expression. So therefore we have your sample signal, which consists of impulses, right? And you are shifting the sinc function to Ts, scaling it, and then you are superimposing this sinc, right? So you can observe is basically a reconstruction is nothing but a sum of shifted sinks, right? So basically what you are doing is that we are doing this sinc interpolation, right? Why sinc interpolation? You are taking each sinc function, shifting in it to n times ts and scaling it by the value of the sample at that instant, and then basically summing up all the shifted and scaled sinc copies, right? So and the interesting properties are the zeros of this sinc coincide with basically the other samples, so it is not affecting the other samples. So the reconstruction occurs at the samples exactly. So between the samples, so between this suppose 0 ts 2 ts, between the samples so the reconstruction the reconstruction is not affecting samples at the locations, at the sampled location. So but interpolation is occurring at the intermediate position. So in the intermediate positions you are doing the interpolation. So we have the samples and we are interpreting these samples to create the original signal m of t, and So this is called interpolation using the sink filter, right? So this is my sink filter. This is my sink filter, right? So this is my sink filter, right? So this is the ideal filter, okay? So this is the basic idea of sampling. So most of the things you already know. I'm just recapitulated these things. I revised these things, and so this is the basic idea. Okay. So now another thing is that I'm going to second aspect of the PCM, a second process of the PCM, and that is called quantization. Okay. So we are sampling the signal. So in the sampling process, we are sampling the signals at discrete time instance. So we have the signal. So we have now this sample can take any analog value, right? So each sample can take any analog value. It can take any value in continuous scale, right? So for the purpose of digital communication, but suppose we want to transmit this sample or digitize it, and the purpose of digital communication, we want to convert it to a discrete set of values so that we can convert it into information bits, right? And these bits can then be subsequently transmitted over the communication channel, or they can be stored. So the purpose of converting these samples, which can take values from a continuous set to values to a discrete set, or to levels from a discrete test, is called quantization, right? So that what I mean is that so we now so we got the samples from the sampling process, and this each sample value is discrete. So we got the discrete time signal. We got the discretized signal in time domain, but their values, their magnitude is not discretized. They can take any value, right? Right. We have not discretized in the magnitude domain. We only discretized in the time domain. So we got the discrete time signal, right? So their values are anything, any continuous value. Now our task is to convert it to this continuous value samples to a discrete, or mapping these samples to a discrete set of values, and which is called basically the quantization. So this is basically the quantization. I would like to so this is basically it's an approximation method, right? This is basically an approximation method, right? So now suppose there are different types of quantizer is possible. One is called uniform quantizer and another is called non-uniform quantizer. So uniform quantizer again could be of different types. The mid-rate quantizer, where the number of quantization level will be odd, and in mid-rise quantizer the number of quantization level will be even. Okay. So here I will discuss only one type of uniform quantizer, that is mid-rise quantizer, where number of quantization level is. I will just give you an example. So other types of the same analysis can be implied to other type of quantization. So here I will give you an example, right? So let's see. So I told you that quantization basically approximation technique, right? So the quantization levels, so so here I am going to give you an example of uniform quantization. So uniform quantization. So uniform quantization. So here the quantization, so each quantization levels are uniformly spaced. That's why it is called uniform quantization. Now consider here that, let's consider an analog signal. This is an analog. Consider a signal like this, analog signal, whose amplitude is defined or confined to in the range minus MP to MP plus MP, right? And so its dynamic range of variation is minus mp to mp, so total 2 mp. Okay, this is the dynamic range, mp minus of minus mp, so 2 mp. And suppose we have used total number of L quantization level, so this range minus mp to mp is divided into L levels. So each of the step size delta is given by 2 mp by L. So step size of my quantization is 2 mp by L, right? Now, so suppose I have used a so I have used a uniform quantizer with total minus 9 delta by 2 to plus 9 delta by 2. So here you are having total 10 levels, 10 quantization levels. So 10 quantization levels. Okay. So this is the thing. So here what is happening? So this is the input output characteristics of the quantizer, which is given by this graph. So you can see that the sample amplitude value is approximated by the midpoint of the interval in which it lies. Okay. So if signal value is, the sample value is, so here you can see if sample value is between 0 to delta, so it is quantized as delta by 2. And if it is, the sample value is delta by 2, between delta by 2 and delta and 2 delta, it is 3 delta by 2. Okay. So if it is between 2 delta and 3 delta, it is quantized as 5 delta by 2, right? Similarly, in the negative side, if the value of the signal is 0 and minus delta, then it is quantized as minus delta by 2, and so on. Okay. So each sample amplitude value is approximated by the midpoint of the interval in which it lies. Okay. So this way this quantization is happening. Okay, it's we're doing the quantizer is discretizing also discretizing the sample value. Okay, so this is the amplitude discretizing method. This is the approximation technique. You can view this as the approximation technique, anything. And why it is called, so this is I told you this is a quantizer, uniform quantizer with even number of levels, 10 levels are there, right? So this is also called mid-rise quantizer. It is also called mid-rise quantizer. Okay, so here 10 levels are there. So mid-rise quantizer, because at the midpoint it is rising. The quantizing characteristic is rising. It is not flat. But if you use a odd number quantizer is odd levels, you can see that will be the quantizer characteristics will be flat in the midpoint. Okay, quantizer characteristics will be flat in the midpoint. Okay, so that is the basic difference. So but the analysis will be completely same. Okay, so this is just one example of uniform quantization. Now now I'm going into the quantization, the next aspect of quantization, that is called basically, now let us look at the notion of quantization error or quantization noise. Okay, So which is very important metric which determines the actually the performance of the quantizer. So we have said that all samples in a particular quantization interval are mapped to a particular quantization level, which are many to one mapping basically, which means there are several values which are mapped to an approximate quantization level. Okay. So what I mean is that so quantization is a many to one mapping, right? Because in which all sample values in a particular interval are mapped to a quantization level. This implies that there is an approximation error in this process, which is termed as the quantization error. So we are mapping a large number of samples. We are basically mapping an infinite number of samples, right? Between two in one quantization interval, there are infinite number of values are possible, right? Because input can be in continuous form, right? Suppose between delta and to delta, there are infinite number of values, and so here you can see, so between delta and to delta, there are infinite number of values can be possible, and all these values are quantized to 3 delta by 2, right? So we are mapping an infinite number of samples or approximating them by a single quantized value that leads to an error, obviously, right? So there will be error, and what will be the error? The actual value of the sample and the quantization level. So in the context of uniform quantization, for instance, we took at the quantization interval 0 to delta, and for this previously considered quantizer with even number of quantization levels, all the samples values in 0 to delta are mapped to delta by 2, right? So naturally, if the sample is 0, we are going to have a quantization error, which is basically the sample subtracted from the quantization level. Here it is delta by 2, right? So basically, you have a quantization error. So our quantization error will be maximum delta by 2 and minimum minus delta by 2. And for each interval, this quantization error will be for each interval, this quantization error will be between minus delta by 2 to delta by 2, right? So this is the thing of so basically, so what we are getting, so this quantization error is, so this quantization error will be so this quantization error is basically distribution of this quantization error. So this is suppose my quantization error, okay, and distribution of this will be minus delta by 2 to delta by 2, so uniformly distributed, and its probability distribution will be like this. That will be a random signal, right? But it will be distributed. So if you take a very simple case like uniform distribution between minus delta by 2 to delta by 2, so this should be uniform distribution for like this, and its magnitude will be 1 by delta, okay. So this will be the PDF, the probability distribution function of the quantization error, okay. So now the power of this quantization noise or error is basically can be computed by expectation of this quantization error square, and that is given by delta square by 12. And I'm not covering the derivation of this derivation of this quantization power, because we have not covered the probability theory in much detail so far. So for this timing, please remember these things. So how we are getting this? So basically remember that my quantization noise is uniformly distributed between minus delta by 2 to delta by 2, and from this uniform distribution of the quantization noise, we can compute the power of quantization noise or quantization noise as delta square by 12, where delta is the step size of the quantization of my quantizers, and so delta is basically 2 MP by L, right? So if you substitute here, you will get the delta by 2 MP by L. You will get I think you will get MP square by 3L square, right? Okay. So basically it is delta square by 12, and if you substitute by delta by 2 MP by L, you can get MP square by 3L square. So that is my quantization noise, okay, power. So associated with my quantization, okay, quantization process. So this is the basic idea of quantization. So quantization basically a approximation technique, okay. So for magnitude discretization or amplitude discretization, okay. So next process in the pipeline is the encoding process. So you can understand the encoding now. Now you got the discretized level. Now our task is to use the encoder, which can translate this quantized sample into a binary sequence, right? So a binary sequence will be produced from this quantized level, and so each sample will be represented by n bits, where n, how we can determine the n will be determined by the number of levels, obviously. So n will be log of L to the base 2, okay. So after encoding we'll get the digital data. So this digital data is basically the PCM signal, and this digital data will be transmitted over the channel by various pulse waveform, okay. So this pulse waveform, we have different types of pulse waveform is possible in digital communication. So I'm not going to cover this part, the pulse waveform, different type of line codes. This is also called line codes in this lecture, but later in digital communication I will discuss these things little bit, how many types of line codes can be used, but basically those are pulse waveforms, some signaling formats, okay. So this is the basic idea of PCM, pulse code modulation. So you can understand that sampling, so it has in the pipeline of PCM, so pulse code modulation, it has 3 steps. One is sampling. So sampling basically converts a continuous time signal to a discrete time signal. Next, quantization, which converts a continuous amplitude sample to a discrete amplitude sample. And finally the encoder actually encodes or it produces a n bit code for each sample, okay. So finally we get the digital data, okay. Now let's do a case study. So basically it is also can be viewed as an analog to digital converter, right? This can be viewed as an analog to digital converter. This PCM also sometimes viewed as an analog to digital converter, okay. So this is the steps. So encoder basically has some analog to digital converter circuit, right? So now let's do a case study, okay. So let's do a case study. So suppose I have suppose I have an analog signal, I have an audio signal, bandwidth 15 kilohertz, okay, about 15 kilohertz bandwidth. So, and I would like to transmit it over a channel, over a communication link, such that in the receiver end I can reproduce, I can reliably receive the speech content from this audio signal. Okay, so in the audio signal it has so many things like music, speech, someone is talking, someone is discussing something, so speech, music, everything is there, right? But my target is that I will transmit it over the channel such a way that in the receiver end I can reproduce we can reproduce my speech content properly. Okay, so intelligibility of the speech should be good, should be significantly good at the receiver end, should be, that is my target. Okay, so it would be, so this audio signal will be transmitted through a low pass filter first, because we know the subjective is, from the subjective is that the signal intelligibility, the speech signal intelligibility is not affected if all the components above 3400 Hz are suppressed. Okay, so maximum speech signal is frequency is 3400 Hz. So means speech speech signal intelligibility is restricted within this frequency range. Okay, so 3400 Hz maximum. Okay, so we can band limit my audio signal. We can band limit my audio signal by using a low pass filter, because up to that frequency the intelligibility of the speech is there, right? Beyond that we don't need, we don't bother about that. Okay, so what do we do? I'm going to use a low pass filter which will make it band limited to 3.4 kilohertz, right? So it will band limited to 3.4 kilohertz, 3.4 kilohertz, right? And then I'm going to sample it by 8 kilohertz by using a sampler with 8 kilohertz, right? I'm going to use a sampler with 8 kilohertz, right? So actually it's band limited to 3.4 kilohertz. So its Nyquist rate is 6.8 kilohertz. So we are sampling it more than the Nyquist rate, so 8 kilohertz, right? So the resulting signal then sampled at a rate 8000 samples per second. So this rate is higher than the Nyquist sampling rate, right? That is 6 kilohertz. So next step is that I'm going to use a quantizer, uniform quantizer of 256 number of levels. Okay, so sampling is done, second is quantization is done, and third step is encoding. So since we are using 256 number of levels, we are so how many bits we need? We need n equal to 8 bits per sample. Okay, so what is the data rate of the PCM signal will be? What will be the data rate then? Data rate will be 8 kilohertz. So I need to transmit 8000 samples per second, and each sample will be represented by 8 bits, right? So 8 into 8000, so 64,000. So 64,000 binary pulses per second is required. So my telephone signal, so if it is a telecommunication system, then my telephone signal requires 64,000 binary pulse per second, 64 kilobits per second. Okay, so okay, this is one case study of the PCM. Okay, so this is the example. Okay, one of the example for your convenience, and that's all for this lecture. And I guess if you have any doubt, please follow this slide, and if you have doubt, please let me know. And in the next subsequent lecture, I will discuss that particularly the transmission bandwidth of PCM, and many other things, that maybe the TDM, the time division multiplexing. Okay, okay. So that's all. Stay safe. Keep learning. Okay. Bye.